Okay, hello finite math students. This is another tutorial video for you. Um, a student in the class emailed me about this particular question in your homework, question number 82. So why don't we work on that? It reads, use a graphing calculator to find a linear regression model for the men's 100-meter freestyle data given in the table on the right, where x is the number of years since 1980 and y is the winning time in seconds. Do the same for the women's 100-meter freestyle data. Do these models indicate that the women will eventually catch up with the men? That's a little bit subjective, but we can try to answer that question. So the men's linear regression model is, okay, so let's work on that. Let me minimize this first. Hold on. Let me launch Mathematica. Okay. New document. Okay. And let me see. Okay, there we go. I'm just trying to resize these windows so that we can look at both of them at the same time. This is a 13-inch laptop, so the screen is not very big. Excuse me. Okay, so I have my Mathematica window on the left. I have my Pearson window on the right. Okay? And let me see. I would like to format this a little. Edit style sheet. Edit style sheet. Input, and we have output. Okay. Input, let's see, show fonts. Let's make it 18, bold. I like Arial. And we could make that, how about midnight blue? Midnight blue. Let's do the same thing with the output. Let's make that bold. Font 18, I think that's 18 pixels, right? 18 pixels, and make it Arial. And we could make that eggplant or midnight, make it the same thing, I guess. How about midnight blue? Okay, midnight blue. And okay, that looks good. And then just close it. Okay, so the first thing I'm going to do, I need my X list and my Y list. All right? So my X list, now I'm going to, okay, so I'm going to do this kind of in a weird way. Now be very careful. X is really the number of years since 1980. So this should actually be 0, right? 0, 4, 8, 12, 16, right? But I'm going to do this a little differently, okay? So we have 1980, 1984. Oops, that's not right. 1984, 1988, 1992, 1996, the year 2000, 2004, 2008. Shift Enter. Let me make sure I have the right numbers here. So 1980, 1984, 1988, 1992, 1996, the year 2000, 2004, 2008. Okay, but what they really want is the number of years since 1980. So this should really be 0, 4, 8, 12, 16, 20, 24, 28, right? So what I can do is simply subtract 1980 from each score in my list. And so now I have 0, 4, 8, 12, 16, 20, 24, 28. It's very nice that we can do that in Mathematica. We can multiply, divide, add, subtract a number from a list, and what will happen is that operation is applied to each element of the list. Okay, that's a nice feature of Mathematica, okay? Okay, so we have the men, this is our y, right? This is, I could call it y, right? But I would rather call it the men scores. I could call it y, but let's call it the men scores. 50.40, 49.80, 48.63, 48.63, 49.02, 48.74, 48.48, let's see, 48.74, 48.48, and 48.17, and 47.21. Okay, that looks good. I have to make sure that my X and Y lists, well, in this case, I'm calling Y the men scores, okay? But it's the same idea. So I have to make sure that they have equal length, okay? What is the length of X? I have 8 scores in my X list, and I should have 8 scores in my men list. Okay, they better be equal, right? Okay, so I'm looking for a regression model. They're looking for a linear regression model, which means, you know, the slope and the y-intercept. Now in Mathematica, hold on one moment, I believe there are several different ways of doing this in Mathematica. Let me think for just a moment. I believe you can use, well, the easiest for you guys at this point might be LinearModelFit. Okay, let me see. I believe the easiest thing for you guys, there are many ways of doing this, but let's use LinearModelFit. So just to make sure I remember how to use this function, I'm going to look it up. Double question mark, LinearModelFit. Shift Enter. Okay, and I'm going to click on local. Okay, so LinearModelFit, these are examples. Let me see. Constructs a linear model of the form. Let's look at the examples. Okay, so this is a really, really good example over here. We have some data right over here, and then we supply the data to the LinearModelFit function. Okay, x and x, these are independent, these are actually independent variables. We can't use that as our independent variable because we're using that to store the numbers of the list. So we could use something else. Make up any letter you want. You know, A, B, C, you know, Y, Z, S, T, any letters that you like. Now, I believe, hold on one second. Let me look at details and options. Okay, this is a little more information than you guys really need. Oops, that's not, wait a minute. 1 second here, sorry about that. Okay, this is a little more information than you, wait a minute. This is way more information than you guys actually need. Okay, so I think we can use this and it should work okay. So the thing is now we're going to have to pair up these points, x and men. We're going to have to pair up those points. So the way to do that, I'll call it data is equal to table x, I'll call it k, men k. K goes from 1 to 8. That's my data. Okay, that's my data. So now I paired up my values. Why am I going from 1 to 8? Because I have 8 points in each list. I have 8 points in each list. So then if I want to use LinearModelFit data, and for this particular, now when you look at the information, when you look at the help information, this can get a little bit confusing. We cannot use X. We cannot use X because we're using it up here. So let's make up another letter. Let's make up another letter. How about, I don't know, T? And we have to use it twice. And we're going to store this in a variable. I'll call it solution. Okay, Shift Enter. Okay. So let me see here. Solution model. Okay, that's not what I want. Hold on one second. Solution properties. Let's make this look a little prettier so I can read this. Okay, so what I want, okay, this is what I want right here, the best fit. The best fit. We can actually get rid of this. I don't need to see all of this right now. So solution, best fit. There we go. Okay, solution, best fit. Round regression coefficients to 3 decimal places is needed. So if I want to do that, round to 3 decimal places is needed, 0.001. Okay, so why didn't that work? That's okay. I'll round it. That should have worked okay, but that's okay. Okay, so here the men's linear regression model is, let's see, 50.107 minus 0.093, and I'm going to have to use X because I think that's really what they want. I can't use X here in Mathematica because I used X already to store these values that represent the years since 1980. But I can go ahead and use, the X value here in Pearson because Pearson and Mathematica are separate. Let's check the answer. Okay, that is correct. Okay, the women's linear regression model. So we're going to do the same thing for the women. Excuse me. We're going to do the same thing for the women. Women, that's equal, okay, so the women's scores, 54.79, 55.92, 54.93, 54.65, 54.50, okay, 58.83, 50, okay, one second, let me make sure I have these numbers correct. 54.79, 55.92, 54.93, 54.65, 54.50, 53.83, and 53.96, and 53.12. Let me make sure I have 8 scores. Okay, 8 scores. So I'm going to do the same thing again. I need to pair up my data because I have each point is made up of two coordinates, an x coordinate and a y coordinate. Okay, I'll call this data 2 table. I don't have to use K. I could use any letter I like. Women, T, and T goes from the 1st to the 8th. Okay? So we're going to do the same thing we did last time. We're going to do the same thing that we did last time. Okay? So we have here solution 2. Let me try something just a little bit different to be clear about something here. Linear model fit data 2. Now over here, what's a little bit confusing for you guys, it's confusing for me too. Why do we have repetition here? Why am I repeating T twice? Okay, why does it have to be used twice? So I really believe this over here, the first T, really represents the form of my model. So I believe I could just do this. I could just do, something like the model has the form A times T plus B. Okay, A times T plus B, where my variable is actually T. I'm curious if this is going to work. No, it won't. Okay. But that's really the idea. Okay, let me see if T plus 1 will work, where 1 really represents any constant, but it's the same idea. Shift, Enter. Okay, so this part really here represents the form of the model, whereas T is simply your independent variable. And this is the plus 1. It could be plus any number, actually. It's simply a constant. It's simply a constant. So solution 2 best fit. Oh, I see. Times 1 plus T, but that's not really, okay. So the model that I really want would be that. Okay. So Shift Enter. Solution 2 best fit, Shift Enter. Okay, so that should be the answer, and Pearson says that we are supposed to round to 3 decimal places. So, okay, let me put my cursor right here. So 55.502 minus 0.30 times x. Remember that Pearson expects the independent variable to be x, but in Mathematica, of course, we're using t. Check answer. Why am I not getting the right answer? Round regression coefficients to 3 decimal places is needed. Did I make a mistake with my numbers? 54.79, 55.92, 54.93, 54.65, 54.5, 58.83, 53.96, 53.12. That's a little bit strange. 0.030. Okay, that's not, it doesn't like that. Okay, hold on 1 second. That should be okay. That is very, very weird. Okay, did I round incorrectly? Let me do a copy and paste. It's possible. Strange. No, the rounding seems to be okay. I can check again. Round. Is it because of that extra 0? But that shouldn't really make much difference. That is a little weird. I wonder what answer... hold on one second. That's very strange. $55.502 minus 0.030x. Let's do a final check here. Okay, so the answer, my answer is 55.502 minus 0.030x. Their answer is 55.502 minus 0.074x. That's interesting. Let me try. That's very interesting that we're a little bit off. I'm not quite sure if I can explain that. Data to TT and best fit. Yeah, that's really interesting. So there's a discrepancy there between Pearson's answer and Mathematica's answer. Let me see if we can figure that out a different way. So okay, 1 second. So if I was going to do this in a more mathematical way, it would really have to be the correlation is equal to the correlation of X in women. Okay. The slope is going to be equal to the correlation times the standard deviation of the women divided by the standard deviation of X. All right, I'm getting the same answer the other way, which it means that Pearson's answer is very suspicious. I have a feeling Pearson's answer is a little bit wrong. And then if I have the equation, remember you have y is equal to the slope times x plus intercept. Okay, you guys remember that? So to figure out the intercept, intercept is equal to y minus the slope times x. Okay, and so what that means is my intercept should be equal to the mean of the women minus the slope times the mean of x. Yeah, so actually I'm going to stand by my answer here, guys. I believe that my answer is correct. My answer, well, Mathematica's answer is simply going to be LinearModelFit, data to TT, best fit. That's really the answer. Now, according to Pearson, my intercept is correct. My intercept is 55.502, but the slope is supposed to be negative 0.074. I don't agree with that, guys. I believe that the intercept, the slope. Pearson and Mathematica agree on the intercept, which is about 55.502. I don't agree with Pearson here. Pearson is telling me that the slope should be about negative 0.074, and I really believe that the slope should really be about, this number right over here, okay, which is about negative 0.030 or negative 0.02958, etc., etc. Okay, so this is where I'm afraid I disagree with Pearson a little bit. I think this could be a mistake. All right, well, okay, but let's continue with the problem. Excuse me, let's continue with the problem. Based on these equations, based on the regression models, will the women's times eventually catch up with the men's times? Well, that's okay. Let's graph the equations. We're going to graph these equations. I think this equation's a little bit wrong, but okay, we're going to use it anyway. Okay, so let's graph these. So plot. Okay, 50.107 minus minus 0.093 times t. I'm going to use t. I can't use x because I'm using x up here. I'm using x up here to represent the number of years since 1980. Okay, so I can't use x again unless I clear it, but I would rather not do that. Okay, and then I have, let me see, I'm going to use their equation, 55.502 minus 0.074 times t. And let's see what this looks like. T goes from 0 up to, let's say 28. Let's say 30. Plot style. So the men's line, absolute thickness, let's make these lines thick. How about the men can be blue and the women's line can be pink. And let's see what we get. Let's see what we get. Okay, so right, this is the women's line. The women's line is in pink. The men's line is in blue. The women's line is in pink and the men's line is in blue. Will the women ever be able to swim as fast as the men? Well, the only way to figure that out really is to find out where these equations are equal. So 50.107 times t minus 0.093. Oops, wait, I screwed that up. Sorry. 50.107 minus 0.093 times t. Is it ever equal to 55.502 minus 0.074 times t? Okay, so we see here that t is negative 283.947, but we don't want a negative number of years. We want a positive number of years. Okay, so according to this negative number here, because we can't have a negative number of years for this particular problem, it wouldn't make any sense. So for this particular problem, we would argue that the women will never be able to have the same swimming times as the men. So the answer should really be no. The answer is no. Okay? Now, why Pearson and Mathematica didn't agree, let me see if I copied my numbers correctly. I'm a little bit tired, so there could have been a problem with that. 54.79, 55.92, 54.93, 54.65, 54, wait a minute, 54.65, 54 point, yeah, 54.50 or 54.5, same thing, 53.83, 53.96, 53.12. So there is a little bit of a discrepancy here. And again, guys, I really maintain that this is a little bit of a mistake with Pearson. Okay, this is a little bit of a mistake with Pearson because according to Pearson, the equation of the regression model is 55.502 minus 0.074x. I maintain that the equation should really be 55.502 minus 0.030, x if you round to 3 decimal places. All right, so that's really what I'm going to maintain there. So I think this is a little bit of a mistake with Pearson for this particular problem. Okay? Okay, but basically that's the general idea. If you're rounding values in Mathematica, for example, round 0.123456789 to, let's say, 4 decimal places, then the answer would be 0.1235. Okay, if you're rounding to 4 decimal places, that's the way to do it in Mathematica. When you're generating plots, I mean, if you would like this to be a little bit bigger, you could make this bigger. Image size, let's make it much bigger, although now we won't be able to see it as well unless I expand my window. Okay, and the reason for plot style, I'm providing 2 different styles because I have 2 different equations, right? I'm plotting 2 different equations. I could make these much thicker, but they're not going to look very good if I make the lines that thick. That's going to look a little obtuse, right? That's not going to be very attractive. So the men's line, let's make that a little, thinner. The women's line, I could also make it dashed. You won't be able to see it that well. Oh, wait a second. How about, there we go. Okay, so I could dash my lines. Let's make that dashed. Okay. I mean, there are a lot of different things I could do with these plots to make them more interesting, more artistic, more informative. Okay? So I hope this helps. I realize that this stuff would be a lot easier to learn in person if we actually met, face to face a couple times a week. Unfortunately, we just don't have that luxury right now because of what's going on in the world. We have a lot of problems now, and for everyone's safety, everyone is now expected to learn and teach online. And I realize it's difficult for you guys, but there's really not much I can do about that. I can control certain things, but there's a lot of things I can't control. Okay, so we're just going to have to do the best we can. And if online learning is not for you, honestly, I'm not sure what to recommend, except, if it was me and I really had problems with online learning, I would, drop the class and retake it maybe next semester or next year when things hopefully will get back to normal. But will things ever get back to normal? I don't know. Right now, we're not living in a very normal world, which is very sad. It's extremely sad. But again, guys, there's not much I can do to change that. I can't control it. Okay, so hopefully these videos are helpful. Mathematica can be hard at first. You just have to practice. You really have to practice. And Mathematica, by the way, has a lot of online resources. There are a lot of online resources that should be able to help you learn the basics of it. You know, you just have to memorize some commands. Excuse me. You just have to memorize some commands. You have to just, you know, wrap your head around some basic ideas. So it's hard, but I don't think it's really that hard. Okay, you know, there's stuff out there that's way harder. Okay, all right, guys. I think we've used up plenty of time, and hopefully you got something out of this lecture. Okay, have a great weekend, and I will talk to you some other time.